if we want to describe the amount of things in a set, that is the number of elements a set has, then we would be describing the cardinality or cardinal number of a set, which is in this case denoted small n, a in parentheses, and in other cases, the one I'm more used to is a reference for the set A inside of vertical bars. I'm not going to use that quite as much here, but I thought I'd mention it because, like I said, it's what I'm the most familiar with. Where hearing that notation, your mind probably either thinks of the Catholic Church or some very red birds. But we should understand here, thinking in terms of the etymology, that this actually does make a little bit more sense. That the word cardinal comes from the Latin, comes from a word essentially translating to pivotal. And so it makes sense that in the church, if you have some very important people, that they might be referred to as cardinal.
Fill them pews, people. That's the key. Grab the little ones as well. Hook them while they're young.
Kind of like the tobacco industry.
Christ, if only we had their numbers.
And similarly, when we're describing sets, we care very much about the amount of things in them. And for that matter, when we're describing numbers, one of the main uses of a number is as a description of a quantity. That's the original use of numbers for that matter. So it would make sense that if we're going to describe something very, very important within a context, we should call it a cardinal value, a cardinality. So when we're talking about the cardinal number, we are in a sense talking about the most important property that a set has. It's the amount of things in it. Where we say that a set is finite if its cardinality is a finite number. So a lot of the examples we've seen here, basically everything other than the set of natural numbers would be finite because you could count specifically the number of things that are in there, and then it's infinite otherwise. Where the exact nature of infinity is a little bit sticky. That describing things in terms of different infinities, it causes some problems, and there's a long and controversial history about that sort of thing, but we're going to focus more on the finite sets. Partially for that reason, also because it's just easier generally. Anyway, when we're talking about these cardinalities, even for finite or infinite things, we're always getting positive whole numbers. You can't have a half of a thing in a set, either it's in there or it's not, and you can't have a negative amount of thing in a set. You can't have the set of negative numbers, you can have sets with negative numbers, but either it's there or it isn't. So a cardinality can't be a negative number, and it can't be a fraction or decimal that isn't, just a different representation of a whole number. A natural number, for that matter. Where infinity, again, it goes off in its own special direction that we're not going to worry about too much. For us, the main things that we want to talk about here are the ideas of equivalent and equal sets. Where, when we're looking at equivalent and equal sets, we say two sets are equivalent if they have the same cardinality. They have the same number of things in them. Where something like that set A from earlier, 5, 6, 7, 8, 9, along with the other set that we defined earlier, I can't remember its name, with the days of the week, Monday, Tuesday, Wednesday, Thursday, Friday, those would both have cardinality 5, so we could say that they are equivalent. For another example, if we look at the set A of states that begin with the letter A, geez, my brace is not good, but we would have something like Alabama, Alaska, let's see, Arizona is AR, and maybe Arkansas is AS. I actually can't remember off the top of my head, but I'm going to say it's AS just for the sake of finishing that. Has the same number of elements as the set of odd numbers that are less than 8. The set 1, 3, 5, and 7. So, these two sets, A and O, are equivalent. Where in a more mathematical sense, we describe this as having a one-to-one correspondence. That is, if you want to think about connecting these two things, we could link Alabama to 1, Alaska to 3, Arkansas to 5, and Arizona to 5, and Arkansas to 7. That's what I get because I don't remember the one for Arkansas. Sorry for the Arkansans who are here watching this. But point is, we could describe a specific connection from one element of one to one element of the other. Though, looking at this, these are not the same thing. They don't have the exact values there. As much as an Alabama football fan might insist that Alabama is the same as 1, it's not. It's a very different description of a very different thing. That is not number 1 in very many things. So we wouldn't say that these two sets are equal. We say two sets are equal if they have the same elements. So, for example, if I have the set B consisting of things... Oh man, that's another terrible curly brace. I'm getting lazier and lazier. 1, 3, and 5. And I also have the set F, which I'm going to write in reverse, as the things 5, 3, and 1. These, it's the laziest curly brace I've ever drawn. That's a parenthesis. Are equal sets. Because like I said earlier, order doesn't really matter when it comes to sets. These are the same things whether we put them top to bottom or bottom to top. So those are the same sets. Those are, as we say here, equal. Where, for one more important piece of notation that we have here, if you want to talk about the empty set, we have that the cardinality of the empty set, n, O with a line through it, is equal to 0. Where only the empty set and things that are equivalent to the empty set will have that cardinality. Because remember, it's the very unique nothing. And that's basically the idea here. Those are the basic pieces of notation that we have to know when dealing with sets, in terms of things like cardinalities, what it means to be an element, how we write an element, and the main 3 ways in terms of descriptions, rosters, and set builder notation that we can use to describe a set. So in 2.2, we're going to describe another sort of relationship that we can have between sets, where we look at things called subsets. That's next.